This lesson is how to find increasing and decreasing intervals in function analysis in calculus. So we have already talked about visually what increasing and decreasing means if you are looking at a graph. Let's talk about the definition of increasing and decreasing. Okay. First of all, for increasing, a function f is increasing on an interval I if f of b is greater than or equal to f of a for all b greater than a, where a and b are in the interval. Okay, that's kind of wordy, it's kind of rigorous, mathematically rigorous. That's just saying, think of this as y, this is like a y2, and this is like a y1, because b is greater than a. So it's like y2 is bigger than y1 on the interval, or equal to, look at what it says here, or equal to, bigger than or equal to. That means we're increasing. Okay? Because of that little equal to, we're actually going to include a boundary if it is on the graph of f. Okay? All right. If y2 is just greater than and not greater than or equal to y1, then we say that f is strictly increasing. Not just increasing, strictly increasing on that interval. And it's very similar for decreasing. F is decreasing on an interval if y2 is less than or equal to y1. And f is strictly decreasing on that interval if y2 is just less than, not less than or equal to, but less than y1. Okay, let's think about this. That's the technical definition of increasing and decreasing. Okay, what can we say about the derivative of f when f is increasing? What can we say about the derivative? Derivative is slope of the tangent. What can we say about the slope of the tangent line when f is increasing? So let's draw a slope here. Here's a slope. Here we're increasing, right? What can you tell me about that slope? Well, it's positive. Is the slope always positive if the function is increasing? What about right here? Is that slope positive? Sure. Is this slope positive? Sure. It's positive until we get to this spot. Okay? Now at that spot where the slope is 0 though, if we are increasing from say here to here we're increasing, right? Well, since the technical definition includes those boundaries, technically we will include those endpoints when we're given an interval, when we are giving an interval. Okay, so what can you say about the derivative when f is increasing? The derivative is positive. What can you say about the derivative of f when f is decreasing? Well, the derivative is negative. So our test for increasing and decreasing intervals, f is increasing on the closed interval a to b if f prime, the derivative, is positive on the open interval a to b. Okay? Now that is assuming that exactly at a and exactly at b our function is defined. There's no hole, there's no asymptote, things like that. Okay? F is decreasing on a to b if f prime is negative on the open interval a to b. All right, it should be noted that a function can be increasing or decreasing where the derivative is undefined. For example, this is the graph of the cube root of x. This curve is increasing for all values of x, even though at the origin the derivative is undefined. Okay? We would still say that this function is increasing for all values of x. Okay? So this test is convenient, but it does not override the definition. All right? This is just a convenient test. All right, a couple of examples. On what intervals, if any, is this function decreasing? And we need to justify our answer. So decreasing will be when f prime, g prime, our function is g, where g prime is negative, is less than 0. So we are going to find g prime and find out where g prime is negative. So the derivative of g here is negative 9x squared plus 6x. Derivative of a constant is 0. We want to find out where, not where it's equal to 0, but where it's less than 0. Well, to anytime you're trying to find where something is positive or negative, use a sign chart. Okay? Anytime in this whole course, we're going to do that. So to use a sign chart, I'm going to first set this equal to 0 and find the zeros. Then I will use those on my sign chart. So I'm going to just factor out an x here. From this one, I get x is equal to 0. From this one, I get x is 6 over 9 or 2 over 3, right? So we take both of those values and we put them on a sign chart in the correct order. 2/3 is greater than 0, so make sure you put it on the right of 0. And we are doing a sign chart on g prime because that's where those zeros came from. They came from these two numbers came from g prime, so we're testing g prime. Besides, we want to test g prime. Okay, let's test a number in this interval. So like 5. I'm going to put 5 into any of my x's in g prime. I'm finding g prime of 5. So it's always going to be very convenient to put it in for the factored form. Okay, or almost always is going to be convenient to put it into the factored form. Notice and remember that we don't care about the value, we only care about the sign because we are doing a sign chart. Okay, so when I put positive 5 in, I have a positive, and I have, if I put 5 in for here, I'll have negative 45 plus 6. That's negative. A positive times a negative is a negative. So to the right of 2/3, our g prime is negative. Okay? Let's test a number inside here. Maybe I'm looking at my equation over here, maybe a 9th. Let's let x be 1/9. 1/9 is less than 2/3 but greater than 0, right? So I'm going to put 1/9 in for this. Well, we're going to keep our positive here because 1/9 is positive. When I put 1/9 in for x here, I get a negative 1 plus 6, and that is positive. Okay? Now I'm going to test this interval. Any number in this interval, maybe a negative 1. If I put a negative 1 in for x in g prime, now I'm going to have a negative from this term. I'm putting a negative 1 in for x. That makes that a positive 9 plus 6. That's positive. We are back to being negative. Do you notice how this alternated signs? We started negative. The next one over was positive, the next one over was negative. Surrounding any zeros, the signs will alternate unless that 0 came from an even powered factor. This factor had a 1. It was only a single factor. But if that was a squared, then surrounding the 2/3, we would have the same sign. So all we have to do is test one sign and then either alternate or don't alternate depending on if we have even powered factors or odd powered factors. All right, let's answer this question. we're looking for G to be decreasing. I will say that G is decreasing on, okay, we're going to be decreasing from negative infinity to 0, including 0 technically, yeah, according to the definition we include that 0, and 2/3 to infinity, again technically including the 2/3. Since we had to justify, so I want to give a since G prime is negative, could have just said G prime is less than 0, on negative infinity to 0 and 2/3 to infinity. Not including those because right at 0 and right at 2/3, G prime is 0. Okay? Next example. On what intervals, if any, is this function increasing? Well, increasing will be when y prime is positive. Yeah, that's my thought process. Again, we need to justify our answers, so we will have a since something at the end. All right. First, we're going to find the derivative and then see where it is positive. Sign chart again. Okay. So y prime is equal to, all right, well, why is this cube root? So in my mind, I am thinking this is 3 minus x to the 1/3 power. Okay, so y prime is, a little chain rule here, 1/3, 3 minus x to the, subtract 1 from your power, that'll be a negative 2/3, times, we're doing a chain rule here, so times the derivative of the inside. The derivative of the inside is a negative 1. So y prime, I'm going to clean that up before I do anything with it. We're going to definitely clean that up, is a negative 1 divided by 3 times 3 minus x to the 2/3 power. Okay? All right. Well, this time we have a denominator. We have a denominator, so I need to examine the denominator to see what makes it 0. So what value of x makes the denominator 0? Well, x equals 3 makes the denominator 0. So that makes y prime undefined. Okay, so x equals 3 must go on our sign chart. In this previous example, the derivative had no denominator, so there was nothing we didn't have to add any additional values to our sign chart. But this time we do. X equals 3 makes y prime undefined. We have to add that to our sign chart. Okay. Now I take my derivative and set it equal to 0. When you set your derivative equal to 0, you are only looking at your numerator. So my numerator is negative 1. And if I set that equal to 0, well, that's impossible. There are no values of x that would make that true. So the only value that goes on our sign chart is the one that made the derivative undefined. So here's our sign chart. Here's the only value that makes, that is a critical number. These are the critical numbers, yeah? So, and this is y prime. The 3 came from y prime. So we're testing y prime, and we want to test y prime. Okay, let's go to the right of 3. If we go to the right of 3, like 4, and put that in for x, 3 minus 4 is a negative 1. The cube root of negative 1 is negative 1, but then we're squaring negative 1, so that's 1. So this is 1, and we're left, so that's positive. 3 is positive, negative 1 is negative, so this whole thing is negative here. Okay. Let's go to the left of 3, like positive 2. Let's go to positive 2. If we put 2 in for x, we'll have 3 minus 2, which is 1. 1 to any power is 1, positive 1. We are still negative. Notice too that this 3 did come from an even-powered root. That 2 makes it an even-powered. So we are not going to change signs around it. Okay? So our function, this y, has a derivative that's negative until 3 where it's undefined. Then the derivative continues to be negative. So this curve, it was decreasing, and then it kept on decreasing after 3. Okay? So where is this curve increasing? Never. Y is never increasing, since y prime is never positive. And that is increasing and decreasing intervals.